Hi, welcome to another edition of Calculus 3. Today we are going to talk about directional derivatives and gradient. This is a very important topic for your future mathematics and science classes, so let's go get started. So as usual, we go back to Calculus 1 to see what was the comparable idea there and come back to Calculus 3. I'm going to go through a short review of vectors because that's what we need in this case. So in Calculus 1 you had a function and you learn about its rate of change. You show the derivative by a variety of notation, and the meaning of that is the slope of tangent line at the point to the graph. So the slope, or this m, is the derivative. And once you are in this situation, you essentially are traveling up or down this curve. There is not much of a freedom, and there's just one number that indicates at what rate you go either up or down. In Calculus 3, in higher dimensions, you are on a surface. You are on a surface, and then you are climbing or descending, and you want to know at what rate you're going to go up or down. Now, when you are on a surface, you have a lot more choices than you had on a curve. On a curve, there isn't much of a choice, but on a surface, like if you are on this mountain, you can be ambitious and try to go for the peak straight up. In that case, you kind of notice a high slope. Or you can go on a spiraling path at a low grade and somehow not exert yourself all that high. So we have a choice. And we want to represent that, and the concept we come across is the concept of gradient, which is essentially a collection of the derivatives. So gradient of a function, we have a function z equal to f of x and y, for example. The gradient of that is written as grad f or del f with this upside down triangle. And the gradient is just a vector, which is a list of your partial derivatives. So if a function of two variables, we have partial derivatives with respect to x and y, and this constitutes a vector for us. That's the gradient of the function. This gradient gets to be used in a variety of applications. One of the most notable one is the directional derivative, meaning once you make a choice according to which direction to go up a mountain, then you have a particular slope. To find that slope, you simply dot the direction vector that you have with the gradient that we calculate, and this is written in two ways, either capital D with a subscript u of f, and it's read as derivative of f in direction of u, or it is written in that style, u dot del f. So to understand this, let's go after two things. One is let's go look at this thing on a picture so that we understand what is it that we are talking about. Then we come back and review vectors so that we feel comfortable handling these kind of entities, and it will be easier to understand the topics that come up. Okay, first up, let's go take a look at the picture that we had seen once before. Let's go to this page by Alfredo Alberca. So on this app, you see a function in this box. You can go ahead and type pretty much any reasonable function here. The graph of that is this blue surface that you see here. We want to study directional derivative for this situation. So first of all, you need to have a particular point in mind. So the point in mind for us is this point here. If you want to play with that, you can, for example, change your x location and y location and choose some different point. Okay, once you choose a point, next you want to decide how you want to climb or descend this mountain. We said you have infinitely many choices. The way we are going to specify our direction is to come down to the xy coordinate plane and draw a unit vector there and say we want to travel in this direction, meaning the way we travel on the surface, our shadow will be this vector down here. So what we do is that we construct a plane that passes through the point that we have in mind and also passes through the direction vector that we have. So this is this green plane here. This green plane is going to intersect this blue surface that we had at the beginning. At the intersection of these two, we see a curve. So this is a curve sitting on this plane, and by directional derivative of this function at this point in this direction, we simply mean slope of the curve that you see on the slicing plane. Okay, so at the end it comes back to the notion of slope you had in calculus 1. We have to go through several steps to isolate it. So again, what happened, you go ahead and choose a surface here. So this is your function z is equal to f of x and y, the blue thing. Next, you choose a point on it at which you are interested in finding what kind of directional derivatives you have. So here is the point that we have. Next, we choose a direction. So the direction is given by typically by a unit vector in some direction in plane. If you want to play with that, here you can change the direction at which you want to do the slicing plane, or you want to climb up the mountain. So given the point and this direction, we construct this green plane. The green plane slices the surface along some curve. You see here something like a parabola, and then on that point, on that plane, at the given point, we go ahead and calculate the slope, and that is what we are calculating here. Now let's go ahead and see how it works on paper when we do it by hand and we calculate it through algebra. So let's go back here. You notice that we talked a lot about vectors, so I think it's a good idea to go back and refresh our memories on basics of vectors, so that when we talk about their applications here, things are going to go smoother and perhaps a little bit faster. So let's go ahead and separate this from our review section. So we are going to review a brief review of vectors. You come across this in calculus 2 and linear algebra and your physics or engineering classes. All of them cover pretty much the same set of topics. So here, let's suppose we have a vector. What's a vector? An ordered list of numbers. So I'm going to write it like this: 2, 3 in square in angle brackets. Your textbook is going to write it as 2 plus 3, and then it writes the unit vectors I and j, which are bold-faced, and sometimes it comes with a little arrow on top of them. It's going to take too long for me to reproduce that, so I prefer this notation. So angle brackets entry separated by comma, just as good, also used in your textbook. So suppose I have another vector, and say this is 4 and 5. And of course, you know, you can have a scalar multiplication. You can take your vector multiplied by some number. It's just you multiply each entry by that number. And if you want to add two vectors, straightforward also. You just add corresponding entries. So I have 6 and 8 and so on. We can combine these two ideas. We have the notion of linear combination. So linear combination, suppose I have these two vectors, multiply one by x, the other one by y, add them up. What do I get? So I get like 2x plus 4y. So multiply this by x, multiply this by y, and add them up. Keep them separate. So 3x plus 5y. And big name is given for this operation, simple operation, linear combination. You see this many places in your engineering classes. It might come under topic of superposition. Okay, next up is the concept of length or norm or magnitude. So we have mathematically it's called norm. sometimes it's called length, sometimes called magnitude. Again, your textbook uses double vertical bar, but that makes my writing here crowded and I think it's unnecessary. A single bar is just good enough. So what is this? Well, what do you think it is? If you have a vector going 2 to the right and 3 up, it makes a triangle, and the hypotenuse of it is exactly what you mean by the length. So the formula is perhaps the most basic formula you get used to from middle school, is the Pythagorean formula. You square the components and you add them up, and that is your norm or length. Okay, next up is the concept of dot product. You see that dot product that you see here is used very often. So to make it general, let's write two general vectors. Say A is A1 and A2. Vector B is B1 comma B2. So you see dot product. So we have here, let's write it, dot product. Also has different names, sometimes called inner product, sometimes called scalar. So dot product, rather peculiar action. You multiply corresponding entries and you add them up. So a final result is a single number, A1 B1 plus A2 B2. So it's called dot product. Okay, so we said that sometimes people call it inner product. Most famous first example of that in your physics classes, you have some kind of force, maybe force of gravity, and an object is going through a displacement, like a ball being shot up or something, and you are calculating the work that is done. So work done, it will be F dot D, and in that context it has the meaning of work performed. So if you see the exact same thing in your physics classes, that is the connection. Now, mathematically speaking, we have a major idea here, is that the dot product is equal to the length of first vector times the length of the second vector times cosine of the angle between the two vectors. So if I have vector A and vector B, and there is some angle between them, let's call it what? Let's call it alpha. Okay, so dot product happens to be product of the two length of the two vectors and cosine of the angle between the two of them. Okay, a major observation here is for a situation where the two vectors are going to be perpendicular. So if I have a vector A and a vector B, and they happen to be in my favorite position, that they are perpendicular to each other, so this is 90 degrees. Well, what do we know about 90 degrees? Cosine over 90 degrees is equal to what? We need a bit of trigonometry here. So cosine of 90 degrees, of course, is 0. That gives us a major clue. Two vectors are perpendicular to each other if their dot is 0, because cosine is going to be 0, this multiplication is going to be 0, and A dot B is going to be 0. So A perpendicular to B is same as saying that A dot B is 0. Of course, there is another case where A dot B will be 0 when one of the vectors itself is 0. But that's, of course, a kind of a trivial side thing. We are not going to dig into that situation. So if it is perpendicular, it's 0, or if you want a small parentheses, if one of the two vectors is 0, then of course the product is also 0. So that's going to be a crucial thing for many of the problems we are going to have later on, mathematical problem as well as physical problems. Okay, next issue up is a particular vector that comes up in our discussion, and that's a concept of a unit vector. Unit vector typically shown by letter U. the claim to fame of this thing is that its length is 1. Well, how did we represent length? Length was, its norm is 1. So what does that mean? Suppose you have a coordinate plane. Say you are at this location, a unit vector, you could be going to the right, you could be going up, you could be going left, you could be going down, but then of course you could be going at any angle you wish. So these are all examples of unit vectors. So if we look at tips of all of them, what do we see? Well, of course we see a circle. This is you get a unit circle, meaning its radius is 1. Unit vectors are used to indicate direction. So if you want to go in a certain direction, you choose one of these vectors and say I want to go in that direction. So specifying unit vector is essentially same as specifying the angle at which you want to travel. Same thing. So remember, if you have a unit vector at some angle theta, this unit vector, you can represent it as its x component is cosine of theta, its y component is sine of theta. That is what you had with your polar coordinates. The same thing here. Now, if I have a vector, let's call this thing A, and then I am dotting it with the second vector, and this second vector I take it to be a unit vector. So I have A times U. Now we said this unit vector could circle like a handle of a clock all around. Let's keep the A in its fixed place. So as I change U, the A dot U is going to increase and decrease and go through cycles. So question comes up, what is the highest value that A dot U can have? What's the lowest value that it can have? What's the middle value? And so on. So we want to do an analysis of A dot U. We want to do analysis of A dot U. For example, what is the highest value? What's the highest value that A dot U can have? Well, let's write it again. A dot U, we said that is A, length of A, times length of U, and the angle between the two of them. Let's call that angle alpha again. So that's going to be cosine of alpha. Okay, the analysis is going to be a lot simpler than what you think. First of all, length of U, by the very fact that we say it's a unit vector, that thing is a fixed 1. So as we go around, it's the same length arrow, and that length is going to be 1. So of course we are holding A in its place also, so that is whatever it is fixed. All that is variable is cosine of alpha. Well, do you remember from trigonometry what's a high and low and middle value of cosine of alpha? Well, when alpha is 0, which means U is right on top of the vector A, cosine reaches its highest value. Cosine of 0 is 1. That's the highest value it can have. So if U is right in the direction of A, we have the highest value. So let's write that down. A dot U is highest when U is in direction of A. Okay, so A was fixed, U is going around. When U lines up with A, we have the highest value. What's the lowest value that this can have? Well, what's the lowest value of cosine of alpha? Do you remember from your trigonometry what angle is it and what value is it? When is it that cosine becomes -1? Cosine of pi, or 180 degrees, however you want to express it, cosine of pi or if you're in degrees, 180 degrees, this is the lowest value. So when alpha is 180 degrees, meaning what? Meaning u has to be pointing in this direction. So this is going to be the lowest value, and this is going to be the highest value. When high is in the direction of the u is in the direction of blue, we get the highest value. When it's direction of red, we get the lowest values. Let's write that down before we move on. A dot u is the lowest when u is in direction opposite of A. Well, what about in between? In between, you could be at 90 degrees, of course. You could have at this two configuration. The middle value is 0, so cosine of pi over 2 or 90 degrees is 0. That's your middle situation. Okay, maybe that's enough review of trigonometry. Let's just note one thing. When it reaches the highest value, what is that highest value? So this is 1, this is 1, and all that is left is just the length of A. So that's what I write. It becomes the length of A. When the angle is pi, this product becomes minus length of A, and at middle we just have 0. Okay, so that was some basics of vectors that we are going to need for our discussion now, and let's move on. So we said we are traveling on a surface, and we want to track how fast we are going up. The central theme in all of these calculations in several sections is the formula we had for differentials. So we said that if you have z as a function of two variables, say x and y, like that surface that we have over here represents the surface represents a function z as a function of variables x and y. Okay, we said if you're at a certain location and you kind of want to move around, you can calculate the amount of movement that you're going to have by using the total differential formula. So total differential formula was, okay, if you change x by a small amount dx, then take the partial of f with respect to x, multiply by how much change you have in x, and then calculate the partial of f with respect to y, and multiply that by the change in y. That's gonna give you the net total change or total differential dz. Okay, now let's go and take a look at the situation we are at. So suppose I am at some location, let's call it x0, y0, and then I'm traveling in a certain direction u. Okay, so that's a unit vector u that tells me in what direction that I'm traveling, and on top of this vector I want to know how the z is going to change. So the rate of change of z as I take my steps in the u direction, that is exactly what is meant by directional derivative of f in the direction of u. Let's go take a look at this picture one more time. Let's see if it helps us. So we said we have z as a function of x and y. That's this blue surface here. We go ahead and choose a certain location. So this is the location x, y, that you can play with this I need to refresh this page. It doesn't stay long enough. So we said you can change your location. Here's I changed my X, for example. You can change your Y as well. You can change the angle at which you are calculating the directional derivative. So this is the U that I'm drawing there. On top of that U, the function is going to change. How do I calculate it? I'm going to calculate dz, that's a change in z, in terms of how much x has changed and how much y has changed. So dx and dy translate in the change in z's, and that's what we are calculating here. So now notice a very simple observation here. I can write this thing as a dot product. This is really fx comma fy as a vector dotted with dx dy as my displacement. Okay, so we have seen this formula before. We just given it a new angle and new point of view. We separate two types of things. One is the partials, that's one type of entity, and the other one is displacements. So we separate these two categories from each other, like oil and water, if you wish to call it like that, and then we give them names if you want. So this one has several names. One of them is del f. Okay, this is pronounced del f. Another name for this thing is grad f. Both of them are going to be used. dx dy, well, that's your displacement. There are several names for that one as well. Sometimes it's displacement of position. So sometimes this is shown as this whole thing is shown as dr. R is position, typically R position x and y, and then dr is differential of position, and you are doing dot of these two. This is a vector, has several components. This is also several components, and you are dotting this thing just like dot of any two vectors. So dr is dx and dy. Now we have another way of looking at this thing. Is okay, these are my displacement. Let's think about it like this. Let's choose an angle to travel at, and then we choose a parameterization along that, maybe dt or something. So when I like a small displacement dx and dy is being employed here, this little vector here, maybe I write it as u dt. So another presentation for this dr is unit vector in direction of the travel times differential dt. So I can use all of these things. We are going to use all of them. So in short, we got dz, let's write it, and then I have del f or grad f dot u dt. We can write it like this now, dz dt, which is the rate of change of z with respect to t. So t is a parameterization along this vector, is going to be del f dotted with u. When you are dotting two vectors, you can write either of them first. So if you want, sometimes this looks better, u del f, so that you get the dot product of two vectors with less confusion as to who is who. So this is going to be the directional derivative in direction of u. In direction of u. Of course, you could specify that you in many different ways. Let's go ahead and do some basic exercises so that we are clear as to what we are doing, and so it doesn't look too theoretical. Suppose I have z. Let's take a simple function, z5 minus 2x squared, say minus 3y squared. Find directional derivative of z at, let's give a location, say let's at the location 2, 1, yes, 2, 1, at point 2, 1, in direction of, okay, we want to give our unit vector. So if I have my xy plane, say I am at location 2, 1, so this is location 2, 1, or let me write it, draw it a bit bigger. Now we have to specify our direction. The direction vector u. Let's say, for the sake of argument, that we are going at 30 degrees with respect to x-axis. So what would be our direction vector? It's going to be cosine of 30 degrees and sine of 30 degrees. So if I have my angle measured with respect to axis in the standard direction, then my vector is going to be cosine of that angle and sine of that angle. So how do we calculate the directional derivative? First of all, I need to have my partials. So I calculate partial with respect to x and partial with respect to y. So if you want to call this thing f of x and y, and then this will be f of x, f of y, but let's just simplify that. Zx, zy. Z with respect to x, minus 4x. Z with respect to y, minus 6y. At 2, 1, zx becomes 4 times 2 is minus 8. Zy becomes minus 6 times 1 is minus 6. So directional derivative of z in direction of u, we said it is zx and zy, the partials, dotted with the vector that we have. The vector I have is cosine of 30 and sine of 30. In direction of, let's write theta is equal to 30 degrees. So I write the numbers. I have minus 8, minus 6, cosine of 30 degrees. We need to know these values, and when you're doing on web assignment, more likely than not, it asks you for exact value, so you have to enter exact values, or it might ask for certain number of decimal places, in which case you do it accordingly. Okay, how do we do the dot of these things? First times first, so that becomes minus 4 radical 3. Second times second, so that's going to be minus 3. And this whole thing is a single number, no commas, spaces and such, is a single number. So how does our climbing go? We are descending because this is negative. If it is positive, we are going up. If it is negative, we are descending. So let's do another example, and then some of the other properties of directional derivatives I'm going to separate it in another lecture. Uh, Suppose I have a function of more than two variables. What then? Suppose I have w is a function of x and y and z. Then what is del w? Well, that's going to be partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, all of them still. So it's red del w or grad w. Let's just pick a function. So suppose I have w is x logarithm of y plus z squared x plus, say, x y z, some mix of peculiar functions. So del w, what is this? Simply we take derivatives. Derivative with respect to x, so that's logarithm of y plus z squared plus yz. Then derivative with respect to y. So derivative with respect to y, this is going to be x with respect to x over y, nothing here, and then xz. Finally, derivative with respect to z, there's nothing here, and I have 2zx and then xy. Notice depending on your exercise, you might be asked to write it this way, or you might be asked to write it with those unit vectors, which has to be picked from so when you write it on WebAssign, be careful that this has to be bold. So unfortunately we are going to be sticklers about that. It has to be correct so that we notice that these are actually vectors. So xy plus xz and 2zx plus xy, if I haven't missed anything. So bold vectors, in handwriting sometimes you put arrows on top of them, but on WebAssign just you choose IJK as bold. Okay, so this is basics of directional derivative and gradients. Now this topic still has quite a few other applications and interesting facts to learn. We are going to postpone that to the next lecture. Until then, good luck and God bless.